Okay, so this is the most important lecture for understanding how you make an image out of an MRI signal. And it's about frequency encoding. And so if you've heard me, you might have heard in MRI you've got frequency encoding and phase encoding. And the goal today is to show you there is no frequency encoding, or alternately said, it's all phase encoding. And a lot of times what happens in MRI classes is they say, this is how frequency encoding works. It's easy to understand. And then they say, well, this is how phase encoding works, and that's too hard to understand because you're not a physicist, and so you'll never understand it. But frequency encoding is actually phase encoding. And so we're just going to start right into phase encoding and just show you why. Don't think of it as frequency encoding. Now, why? There's a good reason. Why do they call it frequency encoding? And I went over this once before, but I'll just quickly review it. They call it frequency encoding because that's how MRI was invented. It was invented by chemists, basically, who, were doing NMR, nuclear magnetic resonance, on chemicals. And then they just had this idea about, we could use a gradient instead. And how does that analogy work? It's a faulty analogy in the end. It's a faulty analogy. It took about 10 years for the MRI physicists to kind of realize what they were doing. And this is something that often happens in science. They get an insight, and then it's a critical insight, and then they charge forward, and then they get some venture capital, and they make make a huge company really quickly, and try to get market share. They don't really understand what they're doing yet, and then after about 5 or 10 years, people kind of figure out actually what they already did. It often happens that way, where it sort of gallops ahead a little bit of understanding. It took about 10 years for people to sort of figure out what they were actually doing. Now, it's what's the original sin? How did people sort of make this initial faulty analogy? Well, it started off with spectroscopy. And so in spectroscopy, what are you doing? You're looking for chemical shifts. So what does that mean? That means you're looking for slightly different resonant frequencies due to the chemical structure. Like if you take acetic acid, it's got some methyl groups in it, CH3 groups in it. So there's a proton H that's stuck next to a carbon, and then you've got an OH group in the carboxyl group, the acid part of acetic acid, and that OH, that's a hydrogen proton stuck to an oxygen. And because those atoms, oxygen and carbon, are different, and they have different effects on the resonant frequency, you can see a little chemical shift in the resonant frequency of the hydrogen that's stuck to the oxygen instead of the one that's stuck to the carbon. So that causes a resonant frequency difference. And so the idea was, the original sort of analogy of how MRI works is that we use a gradient. And what does a gradient do? Well, it changes the resonant frequency. And so it's just kind of like a chemical shift. That's a good analogy. It is. That causes a change in the resonant frequency. And then we stimulate, with an RF, radio frequency. That's the same. We always turn on the RF when we're trying to make an image. And then what we do is we time sample the FID, free induction decay. We time sample. This is the return signal. So we time sample the return signal, and we're doing that over here. We're going to show that you don't have to. It's not really time sampling, but we'll just say that that's a sort of a partial analogy. And then number 4, we do a Fourier transform. And why do we do that? So the idea is that these different chemicals are causing, say like, one hydrogen to oscillate like that and another hydrogen to oscillate like that. And then we add those two together and we get, a signal that's got several frequencies on top of it, equals that. And then we do an FT. And what does an FT do? It separates those things by frequency. So it turns this time signal, into a frequency spectrum. And we just time sampled those oscillations that were occurring right here, 2 different frequencies. We just made a bunch of, samples of this signal right here. And then we Fourier transformed it to decompose it into frequencies. So that's very intuitive. This is the way that, MRI is taught. It's a complete garden path. If you think of it this way, you will never understand how it works right. And so we do an FT, and what does the FT do? It takes our time sample and converts it into frequency, and that separates out the different chemicals. And so the original SIN analogy was, we're doing an FT over here. It turns out we're actually doing an inverse FT, but we're doing an FT over here, and we get an image. And so if you think of it this way, well, let's make one more little table. So here's what's wrong about thinking of it that way. So here's spectroscopy and imaging, and here's what signal we get out, and what is the result. So we just have like a 2x2 table. So in spectroscopy, we have, time sample oscillations. And then we Fourier transform them, and we get a spectrum of, frequency diffs. Usually, we've done phase-sensitive detection, and so we're just getting the difference in frequency as opposed to the actual frequency itself, 123 megahertz. It'll be a much lower number. That's just the difference in frequency between the two different chemicals. So that's the original one. And then the idea here, this original analogy was, well, gradients are just like that, and they just cause things, and then we do a Fourier transform in order to separate out the different frequencies that are occurring when the gradient is on. That's the mistake. And we'll sort of try to explain why that's a mistake. So what's actually going on here? We're not taking time samples. What we're doing is we're taking samples of spatial frequency. It's the inverse. It's kind of the inverse of spectroscopy. So there's the frequency part. Here's the frequency part. So we're taking time samples of spatial frequency, and then we're inverse Fourier transforming it into the object, into a spatial object. And this way of thinking about it was, so back in the day when they first invented this, they didn't call it K-space because they hadn't even really fully understood what they were doing. And so the whole K-space idea of spatial frequency space is something that sort of came after MRI imaging had already been invented. And what's the critical difference? So the critical difference is this is the frequency side over here. That's analogous to this side, the result. And so what we're actually doing is we're not recording time samples of a bunch of oscillations with superimposed frequencies on them, and then doing a Fourier transform to fish apart those frequencies, which then correspond to spatial location. We're really not doing that. What we're doing is we're taking a bunch of samples of spatial frequency. That's our data, and then we're inverse Fourier transforming it to space. So let's just go through this a couple steps of frequency encoding to see why it's actually not frequency encoding. So don't think of it as using a Fourier transform to fish apart different frequencies that were caused by the gradient. We don't want to think of it that way. And what we want to think about it is as an inverse Fourier transform. And we'll see that it's actually a sample of spatial frequency, and we're doing phase encoding. And the only difference with phase encoding, real, like quote unquote real phase encoding, it's just the different axis in which you applied the gradient. That's the only difference between frequency encoding and phase encoding. They're basically the same thing. So the whole idea is we have a gradient on and we're recording some data. That's the fundamental idea of frequency encoding and or phase encoding. But we'll see, you don't necessarily have to have the gradient on while you're recording the data. That's critical, and even true for frequency encoding. So let's start off with our gradient. And so here's our gradient. We'll call it like the GX gradient. So what am I drawing there? I'm drawing over time whatever the strength of the GX is. And what is the strength of the GX? It's changing the Z component as you move in the X direction, which is changing the resonant frequency. So let's start off at a time before we turn the gradient on. So let's also assume we already did the RF. Already did RF. Okay, so I'm not drawing that, but we already did the RF. And now we haven't turned the gradient on yet. And so what we want to do is examine what the phase of the oscillation is across the brain. So we're looking at this in real space. So this is real space. So this is X here. And so now we already did the RF, and what does the RF do is it sweeps all the protons into the same phase. And so let's say we did a 0 degree phase angle, which means like, we started the oscillation exactly at time t equals 0, along the x-axis or the y-axis, whatever you consider to be 0. And now let's just draw a whole bunch of little circles, and the circles are going to contain these vectors of what the phase is at each point. And so let's assume that assume that we're looking down, so here's the, we're looking down on the XY plane, okay? So normally we draw the XY plane sort of like this. Here's like, Y. Here's X and Y like that. So imagine we're looking down on it. So there's an eye. An eye looking down on it. So we're looking down on the XY plane. And since we turned on the RF, all the vectors are lined up like that. It's making a big signal because they're all, so this is the phase of the oscillation. So they're going around 123 megahertz, but around the circle. But this is where they are relative to time t equals 0. That's what the phase means, the phase angle, because they could be like a quarter cycle ahead or a half cycle ahead, but now we're saying there's no cycles ahead, so also known as 0 phase. And this is X. This is actually going across the scanner. Okay, so now what happens? Number 2, we turn the gradient on, and let's just turn the gradient on for a little bit of time, and then record one data point. So that's still time, but now let's just look at what happened to our spins here. So here's another picture of all our spins. So now what's going to happen is say we turn the x gradient on. What's going to happen is, and for the sake of an easy drawing, let's just assume the x gradient starts at 0 and then it gets higher at this direction. So if the gradient is higher, it's going to make the spins precess faster, which means they're going to get ahead in phase. So let's say we happen to turn the gradient on just for exactly the amount of time for these guys to get one ahead. So these guys are one ahead of these guys. And then in the middle, this guy is 180 degrees out of phase. And then over here, this one will be sort of at 90 degree phase, and over here it'll be like 270. And so what will happen is, here's what the state of spin in the brain, will look like. Okay, so we wrapped them all up. We wrapped them all up so they go around like that, and then they get all the way around to 360 degrees, because we just happened to, we calculated whatever gradient we need for the ones at the top end of the gradient to get exactly one cycle ahead. And so if we plotted out the phase of that oscillation across the brain, what we're going to get is it's going to go from like 0 up to 2 pi, 360. So this guy will go all the way up, and then we'll eventually end up to 2 pi over here, like that. So that's the phase of the oscillation of the local proton precessing across the brain. Now, if you look at this, and then what does this data point recording mean? Well, we take this signal out of here, and what do we do with it? We do phase sensitive detection to get the signal difference, to basically measure the phase. It's a very rapidly oscillating signal, but we don't want the oscillations. What we want is what is the phase? What is the phase of these summed oscillations? But remember, like we said, we record from the entire head. We do an integral across the entire head, or you could sort of think of it as a discrete sum across the entire head. And we get one data point out of that. And here's the real part of it, and there's the imaginary part of it from the phase sensitive detection. That's this guy, does that. It turns this data stream into two numbers. But when you look at this, there's a problem here. So if we sum all these guys up, so remember this is a vector sum. It's a sum of all the vectors, of all these spin vectors across space, and this is the RF coil, picking this up, and then we do phase sensitive detection on it, and then we take a snapshot, which is just basically what is the instantaneous vector sum of all those guys. And if you look at this, you can see there's a problem. What is the vector sum of these guys going to be? Anybody see what the problem is? It should come out to 0, right? Because you uniformly change the phase going across. If these guys are all the same length, they're going to add up to 0. That doesn't seem good. That seems like, what can I do at 0? But it's the correct answer if you had filled the entire bore of the magnet with gelatin. So say we had just poured a complete jello mold into the MRI. Lots of protons in the jello. Then when you took a signal out of that jello, you'd get nothing. And what would the image look like? Nothing, just completely uniform. So what's going on? Well, we've actually got a brain in there. And so now let's put the brain in. So here's the actual brain, like that. Because we're going in the x direction. And so, here's your image. And, there's, it's a coronal section of the brain. There's like the basal ganglia, and here's a temporal lobe down here. So what does that look like? Well, it looks like, bright brain and black air. And so what does it look like? It looks like something like this, then it goes up, and then if you just made a line across, and then it goes down. So that's what we actually got in there. So what's going on here? We're just doing a Fourier transform of the brain. So here's the brain. That would be the first term in our Fourier integral. Remember, the Fourier integral is integral of, whatever the brightness of an object is at a point in x times the e to the minus I 2 pi k times x. So where does all that other stuff comes from? Well, from the gradient. And so what the gradient did is it basically just did e to the minus I 2 pi k times x. Now there's a lot of symbols in there, but they all sort of boil down to, this thing right here, 2 pi kx, is just an angle. And so, like, for example, k equals 1. That's what we did. So what I've drawn out here is exactly this thing. This is what this equation here exactly is equivalent to what I drew here. And, what is that equation? It's just like sines and cosines of these unit length 1 vectors. All these vectors are exactly, so that's an angle, and then this whole thing is, vector length equals 1. So I just essentially drew out that term, which is the second term in the Fourier transform sum, Fourier transform integral. So now what do? We essentially correlate that. You can sort of think of it as either just these arrows, or you can think of it as a sine and a cosine. We just correlate that with the brain. Because there's not too many protons over here. And if there are any, their phase of their oscillation is going to be, in 0 degrees, and there's not too many over here. So after we effectively multiply our brain protons times our sines and cosines, what are we going to get? Well, we get like a teeny little vector right here. And this guy, the teeny little vector here, teeny little vector here, teeny little vector. All these guys will be really tiny because there's hardly any protons out in the air. And then when we get into the brain, now we'll have like a pretty big vector because there's a lot of protons in there. It'll be the same angle as that guy. Make it the same angle. Okay, same angle as that guy. And there's a lot of protons here, and a lot here, a lot here, a lot here. And then we're starting to get to not very many, and then back to here. So you can see what's going on is we're actually doing a physical Fourier transform. And so now we're down to the little teeny tiny vectors again over here because there's hardly any protons out there. Okay, so now when we do this snapshot, what do we get? Well, we're going to get a vector that's maybe about like that. Okay? And it will have some, imaginary part and some real part. The real part happens to be negative here. So that is one data point. So this is one data point, which is equivalent to spatial frequency 1. So spatial frequency equals 1 content of entire brain in the x direction. So that's our single data point. And what is it? It's actually just the physical computation of a term in the Fourier transform sum. It just takes e to the minus blah, 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 which is basically just sines and cosines, like a sine and cosine of frequency equals 1, spatial frequency k equals 1, and then multiplied by the brain, and then summed up. And so the reason you get a signal out of it is because, you know, the vectors in the brain are sort of pointing more or less to the left, and the vectors out in the air are pointing either up or down, and they're much smaller. Okay, so that's our spatial frequency 1. What about spatial frequency 2? Because we've got to collect a whole bunch of different spatial frequencies. So here's a little bit later in our, so here's our first time point, and now we leave the gradient on for exactly the same amount of time and record another data point. So here's time going that way. It's still the gradient x going that way. So now what happens? So now we've got another set of circles, and all we did is we just basically made 2 wraps and spins. So now what's going to happen is we left the gradient on for twice as long, so that means that this guy's going to be 2 ahead. And then in the middle, where this one was 180 degrees, it's only going to be 1 ahead, and then it's 0 ahead here. And so, you know, it's going to be going that way, so, you know, up here, and then, you know, down here. So it's exactly the same as before. We just wrapped it up 2 times. And so now we're going to, you know, go up to, you know, reversed there, and 90 degrees there, and 270 degrees there. Okay. Okay, so what does that look like if we plot out the phase of that? It just looks like 2, so it's still going between 0 and 2 pi, 0, you know, equals 360. So there's the phase. So now what's going to happen is halfway through, we're going to get back, we're going to go up to 2 pi, and then back down to 0, and then back up to 2 pi, like that. 2 pi over here. So then what do? We take another snapshot, and now the question is, does the brain look much like this? Not as much. It really looks like this. It really looks like spatial frequency 0, spatial frequency 1, because what does it actually look like? It looks like let's put a cosine on there. So let's put a cosine. So here's a cosine. So a cosine looks like this. That's a cosine. So this is cos of 1. So it really looks like that. Now, you might think, well, it doesn't look like that. Well, it actually looks like it's negatively correlated. It's strongly negatively correlated with the cosine of 1, because it's kind of like, it's negative where the brain is positive, and where the brain is negative, it's positive. And so that's, if you do that correlation, that's a very strong correlation, which happens to be negative. So it looks a lot like that. How much does it look like a cosine of 2? Not as much. So a cosine of 2 is like something like this. Doesn't look much like a cosine of 2. The brain looks a little bit like it. If there's a bump in the middle, but then you've got these bumps out here which don't look like it because there's just black out there. And so what do you do after that, etc.? You just keep going a long time. So you got to collect tons of data So this is just like 2 data points. So if we leave the gradient on for a long time, I haven't drawn it quite to scale. So say we record a data point over here. What does that look like? I'm not going to try to draw out the arrows. We'll just draw out the phase, this phase plot. Here's the phase plot. So if you draw out the phase plot, there's going to be hundreds of wraps. You can wrap it up like 128 times. And so if we plot out the phase is going to start at 0, ramp all the way up to 2 pi, and then go down to 0, ramp all the way up to 2 pi, down to 0. So like this is what I call these stripes. So you just stamped on, etc. 256 stripes. So that means these guys are all wrapped around. So this guy, at this end, the guy might be 128 cycles ahead, a lot of cycles ahead. And then you take another sample of that. And so this one is 1 data point, spatial frequency 1. This is 1 data point, spatial frequency 2. And then this might be like spatial frequency 128. Spatial frequency equals, k equals 2. And this is, spatial frequency equals 117, say. Equals k equals 117. Okay, so, and again, each time we just have to sum over the entire brain, sum over the entire brain to get that, so sum over the entire brain to get that result. So you can see, so it's phase encoding. You're just messing with the phase and then recording these sums of phase. There's nothing in it about the peeling apart different frequencies by recording simultaneously present different frequencies over time. That isn't part of the picture. And one way of seeing that it's not necessary to have different frequencies on at the same time that you're recording the data is to record the data in a different way. So you could we could turn on the turn on the gradient like that. And one way we could record data is just leave the gradient on, frequency encoding, leave the gradient on and record data points with the gradient on. Now in that case, at each point in time, there's multiple frequencies because the gradient is on. It's causing different parts of the brain to resonate at different frequencies. This guy's a higher frequency than this guy over here. And so at first you might think it's kind of like a spectrogram of some resonating chemicals that are resonating at different frequencies, and you're recording the signal over time and you're trying to fish apart their frequencies. You might think that way. And that's the way that a typical MRI course will sort of garden path you into thinking. But it turns out the reason that can't be the right answer is if we just turn on the gradient for just this little bit right here, I made it a little bit too big. So just turn the gradient on for that little bit, turn it off, and then record a data point. We get the same data point. And then turn the gradient back on again. So this guy corresponds to the first little chunk here, right there, and this guy corresponds to the second little chunk right there. And then record another data point with the gradient off. So as soon as you turn the gradient off, the frequencies all go back to the same as they were before. So here's another data point and another data point. That turns out to be the same. So that shows you that it's not working by recording a signal with multiple frequencies in it and then using a Fourier transform to separate them. That's not what's going on. Because In this case, you've got the gradient off, and the frequencies are all the same, and you recorded a data point, and then you turn the gradient on, turn it back off again, record another data point, frequency is all the same again, and you got the same thing. So it really had to do with sort of the way you were tweaking the phase, not the fact that you were recording a signal that had multiple frequencies in it. Now, it's very efficient to do it this way because you just leave the gradient on, and it happens to be the case that there's always multiple frequencies in there. But really, when you think about how the data is being collected, you're just taking an infinitesimal sample. So what's happening is you're just taking a phase snapshot. So you're really taking, you're taking a phase sum snapshot, and that's really what's going on. It's not fishing apart frequencies caused by the gradient that are in different parts of the sample. That's how you achieve the phase distribution, but that's not how it fundamentally what the Fourier transform is doing. It's doing this inverse Fourier transform. So if you can understand this, then phase encoding is exactly the same thing. Because what's phase encoding? Usually in phase encoding, so this is frequency encoding. There is no frequency encoding. So this is frequency encoding. What's phase encoding? Well, phase encoding is just turn on a gradient before you do the, so this is, phase encoding. So phase encoding, and what's the thing that really distinguishes phase encoding? Well, it's the fact that it's a different gradient. So here's the x gradient, and this might be, say, the y gradient. That's the thing that's really different about it. And also, it's different that you do it before you start recording data. But you can see that, by doing frequency encoding this way, it's just like phase encoding. You just turn the gradient on for a little bit, just like you're doing phase encoding, and then you recorded a sample with the gradient off. Like all the phase encoding points are all recorded with the phase encode gradient off. But you could have done that with the frequency encode gradient too. So you can see there's no difference between them. So there is no frequency encoding. It's all phase encoding. So what does this, look like? Why do I call it stripes? So, what does it actually look like in the brain? So we're visualizing what's going on with the phase of the spins in the brain. So let's just draw, why do we call it stripes? So let's just draw our image. So here's a coronal section of the brain. There's the hippocampus down here. There's some gray matter, there's a ventricle. Complicated image, yeah. So what does spatial frequency 2 look like? So spatial frequency 2 is going to be, say here's where the spin phase wraps. So if I draw out the spin phase as color, you can see here's where the spin phase is 0. And of course it's out in the air, so there's not many protons there. And then the spin phase, slowly goes up to 90 degrees, and then it's about 180 degrees here, and then finally gets up to 360, wraps around, and so it's back to 0 here. And so, what are the gradients doing? What they're doing is they're not, the key point isn't that they're causing things to resonate at different frequencies, although that's obviously how this effect occurs. But what you're really doing, you should think of it as you're just stamping on 2 stripes onto the brain and multiplying by the brain. That's what, so we're physically doing the Fourier transform by taking some e to the minus I 2 pi kx's, that's the stripes, and stamping them onto the brain. There's the brain. And then multiplying those two, that's kind of what, weighting it by how much stuff is there. And then we're taking a snapshot. And the snapshot is the sum. It's just the integral across this entire thing. So we just add up that whole thing, just sum the whole thing up, and we get one data point. We get one real and imaginary data point. So there's, the imaginary part, there's the real part. And what does that data point tell us? It pretty much tells us how much does the brain look like two stripes. Now, that doesn't seem like enough information, and it isn't, because what you've got to do, in addition to doing like all different kinds of, vertical stripes, so here's like, how much does the brain look like 4 vertical stripes, and then you could also say like, how much does the brain look like, 27 45-degree stripes, and how much does it look like, some negative frequencies. What does it look like, how much does it look like 67 slightly less than negative 45-degree stripes, etc. So you're going to need as many stripe patterns as you have pixels. So here's your pixels in your brain. You need just as many stripe patterns as pixels. So you need all different spacings of stripes, all different rotations of stripes. So you need a lot of data. So like for one slice, like 256 by 256 slice, you need 65,000 data points. This is only one data point, so you need 65,000 of these guys. So that's frequency encoding. So it's not frequency encoding, it's phase encoding. Okay, so I stopped before, so there's got to be, this is the most important lecture if you can understand this, then you can sort of understand how images are made, and you can understand phase encoding because it's exactly the same. You already understand it. So let's just take some questions. There's got to be some questions. So we haven't constructed the image yet. Of course, we've got to do the image reconstruction. We just collected the data on it. This whole thing is like how we collected the data that we need in order to make an image, but we haven't made the image yet. So just make sure that we're just talking about sort of the encoding part. How did we do a Fourier transform on the brain? And so basically what it is, just there's nothing to it, just a gradient, and turn on a gradient, record some data, you're done. Okay, there's got to be some questions about frequency encoding, or what some of these things mean, like the phase, what the circles mean. That just means like this is all, MT. We're talking about this is M. All these things are MT. State of the transverse magnetization across the brain. And this is all X. Yeah, this is real space here, not K-space, all real space. Come on, question or two. It was so clear that I highly doubt that. Got to be some confusion. You might have gotten lost toward the beginning. It's okay. Any questions? Yeah. Okay, what is this? Yeah, what is the stripes? So you can think of this as just like one line across the image. So if I just take one line across the image, so like here's X and Y in the image. So let's just pick one line and look across the image. If you're on this part of the image, the gradient is 0. We're just assuming that the gradient started at 0 at the left. And then as you go across the image, the gradient gets stronger and stronger and stronger and stronger, just linearly going across the image. And so what does the stripe consist of? It consists of a stripe of phase. And what does that mean? That just means you've got some protons oscillating at 123 megahertz over here, and over here they're oscillating at 123.1 megahertz. It's less than that, but they're oscillating at a slightly higher frequency, which happens to just be the right frequency for them to get one cycle ahead of these guys. So when you first turn the first instant of the gradient on, they're all oscillating at the same rate. And then you turn the gradient on for a little while. And this guy goes a little faster until at the end of the time where you record the data point, this guy is exactly 1 cycle ahead. And so I call that one stripe of phase going across the brain. And then it gets weighted by like where the brain is, because there's some protons in the air here around your head, and they have 0 phase. And there's some protons over here in the air, and they also have 0 phase. Because in this case, they were like 2 cycles ahead. But obviously, there's a lot more protons in your brain, and so the total signal coming out of the brain is going to be a lot bigger than the signal coming out of the air. That was like, represented by the length of these vectors in the 1 stripe condition. And this was the, this was the two stripe condition. And so I call them stripes. They're not really black and white stripes because they're complex stripes, right? Because they've got like, a phase angle. There's a real and an imaginary part of it. And so it's basically just what the stripe is stripes and angle of the phase of the oscillation. And what's the phase of the oscillation? It's just like you define some time, equals 0, and then you say at this point, what is the angle? What is the angle of the spins? And if at this point the angle of the spins was 90 degrees, that's a 90-degree phase relative to time t equals 0. And of course, say this amount of time was the amount of time it takes to go one cycle, you could have phase 0 here again. So phase just means, where the spins are around the 360 degrees of transverse magnetization. And stripes just means how many cycles are you ahead at, so here we're 2 cycles ahead. So this guy is, not ahead, not ahead at all. And this guy is, 1 cycle ahead, which looks exactly like a not ahead at all. And this guy's 2 cycles ahead, which also looks like not ahead at all. And so I call this 2 stripes. Is that? Yeah, and the gradient, since the gradient is very uniform, it can sort of stamp on perfectly vertical stripes if you turned on the gradient in this direction. Now, there's a little question of like, if you turn on another gradient, what's it going to do to the stripes? Say I turn, so these vertical stripes were caused by turning on the gradient going in the x direction. What if I turned on the gradient going in the y direction? You would get some horizontal stripes instead. What if I turned them both on? Or I did something like this where I first turned on the phase, I turned on the y one first, and then I turned on this one. What's going to happen? Well, it's going to rotate the stripes. We'll come to that on Monday when we look at like how do multiple gradients interact with each other. It causes the stripes to rotate. But this gives you an idea how it's possible that you could reconstruct the brain from data points that come from the entire head, because you're going to have 65,000 data points. How much does the brain look like? 96 stripes that are tilted this way. How much does it look like? 45 stripes that are tilted this way. There's like 65,000 combinations of those, of all different spacings of stripes and different rotations of stripes. And from that information, that's how we can make an image that has all these tiny little voxels in it. Okay, there's still time. One more question. Yeah.
Why are the phases represented in the circles?
Like this guy here?
Yeah, and then on the last one.
I didn't draw them in the circles, but the reason I can't draw them in the circles is because I need so many circles, because they already went all the way around. They already went like all the way around 360 degrees by the time you got to here. So I would have had to have like made a diagram like this, but it has to fit into this space here, and then I need another 128 copies of it.
Is that because it's happening faster?
Yeah, it's happening faster in space, right? It's happening because this is x, this is the x direction. So the idea is that we hit it with the RF. So the RF did this. The RF lined them all up. So they're all lined up. We slam it with the RF, they're all lined up. Then we turn the gradient on just for a little bit. So this picture is after the gradient was just on for a little bit. And that little bit of time was just enough to get these guys one ahead. And then we leave it on for another little bit. And then that was enough to get these guys two ahead. And then we, leave it on for a long time. And then that's enough to get these guys at this end like 128 ahead. But it's all nice and uniform, because there'll be exactly the place where it's like one ahead, two ahead, three ahead, four ahead. They'll all be exactly perfectly spaced across the brain. Every millimeter or every 2 millimeters, it'll get another cycle. Say it's every 2 millimeters. So like, if this was like 0 millimeters and then just 2 millimeters into the brain, we're already one ahead, and then 4 millimeters into the brain, we're two ahead, and then 6 millimeters into the brain, we're 3 ahead, etc., all the way out to the edge of the brain. So this is like a stationary snapshot of how much ahead the precession is. There's got to be some other questions. It's the most counterintuitive part, just to see how many cycles ahead you get. So you can get at the end of your data recording, you could be easily 128 cycles ahead of the other end of the gradient. But it's very precise because the gradient is it's making these perfectly vertical stripes of phase of the spin. And there's nothing stopping it. If you record long enough, like you take a dead brain, put it in there, record for 24 hours, you can make teeny, teeny, tiny little stripes that are like, 1/10 of a millimeter. No problem.
So what determines how fast is precessing?
Precessing. Okay, so that's a good question. So what determines how fast they get ahead is just the area of this. So like, how strong was the gradient and how long did you leave it on? So, and what is the area? The area is, just equal to, time on, times strength. So if you leave it on longer, it'll get further ahead. If you make it stronger, it'll get further ahead. So you got to consider both. And so I didn't say how we calculate that, but basically I just said, let's turn it on the amount of strength and the amount of time that it takes together to get us one ahead. But if I just doubled that amount of time, I would get two ahead. Or if I just doubled the strength of the gradient, I would get two ahead instead of one ahead.
But how fast it is ahead is based on where in the brain it is.
Where in the brain it is, because the gradient is different in different parts of the brain. Yeah, because like you just assume the gradient at this point is 0, so you haven't added anything to the z component, and at this point you've added just enough to cause the precession to be faster, so that at this particular time point you're one ahead. Because this thing is you're recording this snapshot just at one point in time, just an instant in time. So you just make a snapshot, like the signal equation, snapshot of the state of all the magnetization vectors. And what is the state? It's just the sum of them all. The complex sum of them all. So like vector sum, tip to tail, add them all up. Any other question? Question? Frequency encoding. So you can see it's just, the physicists, they call it, spin warp. You're warping the spins. Warping them. And what are you warping them into? You're warping them into these repeated stripes. Yeah, and so and you don't have to think about frequency encoding anymore. There is no frequency encoding. It's all it's using the increased precession frequency to mess with the phase. That's what all MRI imaging is. Okay, any last question there? Yeah, it's a strange world, strange Fourier world. So, any last one? All good? Any questions? Okay. Okay, so on Monday we'll talk about phase encoding, which is basically going in a different direction. So how, if you put two gradients on, how do they interact with each other, and how come that doesn't mess everything up? So how can you get a 2D image? Because all the stuff we're doing here, you could just sort of think of it as just one line across the image, but we want a whole image with 2 dimensions in it. So how do we get that? Okay.